So, so here kind of each connection has a node and it has a weight, right? So the way we do it is like if we want to hook up YYZ and LAX, let's say with a connection with weight 1000, then what we do is our YYZ, so it's like YYZ has connections, right? And then YYZ connections are basically like this list that looks like this, right? So one is like con LAX 1000 and another is like this. So what is this? So like if you were to say something like A is equal to this, then you could say like A node, and this would be LAX, and you could say like A weight, and that would be 1000. You could also just say like YYZ dot connections 0 dot node is LAX. Does that kind of make sense?
Yep, thank you.
All right.
Would you mind just clarifying what imports we're allowed to use for Python?
None unless they're specifically allowed. So you should like there's no reason that you should be like learning kind of. I don't think there is any reason to be like learning like, oh, like what if import this, what if import that. So it's like the midterm, right? So like by default, nothing is allowed.
Okay, thank you.
So there is like there is a question where like something is like technically allowed, even though you could like even though you don't really need it, but I'm allowing it anyways. But most like everything is banned.
Just two quick questions. Um, first of all, I was doing the 2012 exam
Okay.
that you posted on ESC 190, and
I
you said
posted the
that,
link, but yeah. Yeah.
and one of the questions that you asked, you said you recommended us do was 1I,
Okay.
which said yeah, it's the array in part H
Okay, that
over
yeah,
Maxi.
that was so that should not have been included.
Okay, so basically, just to clarify, there's nothing on heaps unless it's like a priority queue. Like no
And
name.
even priority queue, it's just a name, right? So like there is nothing about heaps as such. So like
Okay.
it's like you can use a priority queue by like importing a thing called heap queue, but that's like as far as you're concerned, it's a name, it's nothing else.
Okay. And second question was also the 2012 exam. Question 2.
Mhm.
I couldn't really figure out how to do it, but I kind of just got to it. My bigger question was, what does assert mean? And are we supposed to know that? And how to
Uh,
use that?
I think we might have like very briefly mentioned it in 180 in Python. So assert just means that you are sending in a value that's true or false to this function, and then the program is just going to stop if the value you send is false. So the way you use it uh, is that if you know if the malloc returns 0, then you can just say like assert it's not 0. And then if it is 0, the program will just stop. So it's like another way to do error handling, which we have not done in C in this semester.
Okay, but I remember in like if you go to question like 1B, I think it is, they used assert for a function, and I think the question was like, oh, why does it not work? Even though they had the assert function. Yeah, this one. Why is it
Yeah.
that in this case there's a runtime error then?
Um, So I don't think it's about the assert. The assert seems fine. Here I think it's because it's struct node star when really it should be struct node because you're trying to store a struct node, not like a pointer to struct node. So the size off here is the wrong size, and that can cause errors.
Okay. Okay, thank you.
Yeah. So specifically, like when you're trying to do like value next, so like if you actually need more than, which you do. So if you need more than just like the amount of space to store the pointer, then you can't store like both the value and next. That causes like a segmentation fault.
Okay, thank you.
Mhm.
And that's just because a pointer has its own size. It's not the size of the actual struct, right?
Well, I mean, yeah, like in this particular case, actually, like the size of the struct is probably strictly larger just because it contains a pointer and then it also has an integer. Or we're just hanging out. Nobody's asking anything. Oh, there's like something in the chat, maybe. Okay, so what imports are allowed in C? So any standard library in C is allowed. So anything that we use that works on ECF is allowed. Unless kind of specifically banned. The rationale there is that you can't really do anything in C without including something like stdio, stdlib, whatever. And there's like not very many things you can do. Whereas like in Python, there's a huge library that you can in principle import, where kind of knowing, like the details of the libraries is like not the point of this class.
Professor,
Hmm?
how much like string and char content do you think will be on the exam? Are you allowed to tell us that?
I don't think anything. How much string and car?
Like stuff similar to like the midterm and project one.
I mean, like that was more than half the class. So okay, like I can so like yeah, I can't really say anything because yeah, like then it'll never end.
Okay, thank
Uh yeah, like I would also say like look at like recent exams. I don't think you would, so like I made up some new questions and stuff, but I don't think you would be like, and like if there's never like, like 100% consistency, but I don't think you would be like amazingly surprised at like what's in the exam. Uh, so yeah, you can include whatever you want, yeah, like in C. In layers, yeah. So so first of all, just computationally, So this would be like a network without a hidden layer. And what we do is we just compute this layer as, a weighted sum of the x's, and then like transform it to sigma, but basically a weighted sum of the x's to z1, another weighted sum of the x's to the z2, and so on. So when we're doing a hidden layer, what we're doing to compute the final output is we first do exactly the same thing we did with the z's, but with the h's. So each h is, this linear combination of the x's with like sigma after that. And then we then treat the h as if it were like the new input. So like we, again, compute the z's by computing linear combinations of the h's with different weights. Does that make sense, just like computationally? So the program, so it's determined is maybe not the right way to say it. Like the program, so like one way of thinking about it is this neural network is just this formula, right? So like you have a way of computing the h's, and then once you've computed the h's, you have a way of computing the z's. So what really changes is the w's, right? So if you change the coefficients w or the weights w, then what the network outputs changes. Okay, so so that's just like computationally what it means to have a hidden layer. Now, the intuition for why you might like to do that is that it might be that the computation is kind of difficult to do with just like, you do a linear combination of the axes and that's your output. So maybe you compute like an intermediate result, and you can think about the vector of the h's as an intermediate result that you compute before you compute the final result using the intermediate result. So when you're training it, so the h's change when you plug in new x's, right? So the h's are computed just like this. So in a way, like for a fixed x, if the w's are changing, the h's are changing as well. But that's like for a fixed x. Without the fixed x, there is like no sense in which there are even any h's, right? So like the h's only exist if you can plug in the x's and compute them. So like just this formula, right? So there is so kind of this part of the network corresponds to this formula, which is saying that like, h1 is equal to x1 times this weight plus x20 times the weight that connects x20 to h1 plus x for 1096 times the weight of this edge, right? And you can just think about it as just a visual representation of this formula, right? So it's not that the h's are determined, it's like they're just computed. There is a formula, which is represented using this graph.
So could we think of the H's as like a filter that filters out all the bad information and then only keeps the stuff that, or keeps most of the stuff that gives the most promising output?
So I would not say like bad, good information. So like in fact, and maybe that's why you're asking, like in some kind of specific network architectures, the H's are referred to as filters, in fact. But it's not like good or bad. It's that it might be that H1's job is to compute one kind of attribute of the input, and H3's job is to compute another kind of attribute. And it might not be good, bad. There could be just different. So like maybe H1 is high when you see like a particular shape in a particular location there, and then H3 is high if you see another shape in a different location, right? So they might both be computing like valuable, just different information.
So does that mean the weights that correspond, like the first level of weights there, does that mean they correspond to a certain like feature of the photo?
So kind of philosophically speaking, yes, like a feature would be like any kind of property, right? So in a sense, kind of by definition, like H1 is a function of the X, so it computes some kind of feature, maybe not a meaningful feature, maybe like not the kind of feature that you would necessarily be able to see with just the naked eye, but in some sense, yeah.
Thank you.
Yeah. So the question is like the bias term. So again, like this is just like how the H's are computed. So what you're doing is you're computing this weighted sum of the X's, or like if you like the dot product of the X with this part of the W. And then when you're computing H1, you add the corresponding B. So for H1, it would be B11. And then you compute sigma of all of that, where sigma is a monotonic nonlinear transformation. That looks where's my picture of the sigma? That looks like this. So the way to think about it, and like I don't really want to like go into like the philosophy of like why the bias is there, or like the math of why the bias is there. Like there's good reasons to do it. But like the way to think about it is you have this big formula where you get to adjust the coefficients so that you get the outputs that you want. And part of what you can adjust is the biases. How would a neural network question be structured in the exam? I would say I could. So like the problem is like I know the answers exactly and I can't tell you, unfortunately. But you know, so I can only answer like in hypotheticals about like what could be, and like what you're suggesting, like those could be questions. Both of those could be questions. I can tell you that there's only one question about this entire slide deck, so can't be both of them. Is what I can tell you. Uh, so essentially both W and B are terms we feed to so training the neural networks means finding the parameters W and B such that the output on the training set are correct. So it's not that you feed W and B to train. It's that W and B, the training process is the process of finding the coefficients W and B such that the outputs are correct most of the time. Yeah, Allison.
Hi. So what does it mean for there to be like a bias value associated with each X?
There actually isn't a bias that's associated with it X. There are ones that are associated with H and Z.
Okay.
It's like just this. So when you're computing HK, this is the formula. So when you're computing H1, you're computing this dot product, and then you're adding B11, so it's like this B11. And then when you're computing Z4, you would also add that B24 over here when computing Z4.
Okay. But like, why do we add it? Like, why doesn't the weight, like, is it like correcting the weight a little bit more?
So so that's like a good way of thinking about it. It's like adjusting this dot product. Yeah.
Okay.
So one way to think about, so like if you want kind of one kind of intuition that you could imagine is let's say that there is like, you know, like there are weights such that like Z1 is high when it's person 1 and Z4 is high when it's person 2 and so on. But then you happen to know that actually it's like really rarely Z4. So even person 4. So even if it kind of looks like person 4, it's probably not. So one way to kind of correct for that kind of prior information is to make B24 like negative, so that Z4 is not too high, even if otherwise it kind of looks like it's person 4, unless you're really sure. So unless the dot product is so high that it like cancels out the bias. So that's like one way to think about it.
Also, I'm kind of confused about like the X's. So if it's a 64 by 64 image, then there's like 4096 pixels. So then,
Yeah, that's just 64 squared, yeah.
so then is it like every X value is one pixel value?
In a grayscale image, yeah.
So would you like, but like X1 would still be 64 by 64? Like a matrix
No,
64 by 64?
So the X's are pixels, right? So you have an image that's 64 by 64, right? And then you just take like every pixel value there. So there's like 64 squared, so 4096 pixels. You plug in like one image that's 4000 something pixels.
But then how do you dot product a single value with weights, which I'm assuming is
You
a
don't. You
matrix?
dot product like the X is the whole thing, right? So like the X is
Right.
equal to like the vector x1, x2, and so on, x4000. So it's like a 4096 dimensional vector. Right? So like
Right.
if you go back, so this is kind of like the sigma notation formula for this, right? So it's like W1JK times XJ sum over all the possible J's. And then what we're saying is like, if you take X to be all the XJs, so this kind of 4000 dimensional vector, and then you take W1JK for every J to also be a vector, then you can think of this sum as a dot product.
And then we add the bias as an n, and the bias is also like a 4096 by one vector.
No, the bias, well, so the bias is not nothing like 4000. So there is like one bias that's associated with each unit. So X's ordinarily would not have biases. H's and Z's would. So here, if you have like 6 Z's, you would have like 6 numbers that are like the biases associated with Z. You can think about that as like a 6-dimensional vector as well, if you like.
Okay. So this equation, is that only applicable to the training data? Or is that
No, so that works. That works for anything, right? So the idea is that on the training data, we know what we want the Z's to be, right?
right?
Because we know the correct outputs. If the axes correspond to the pixels that depict person 1, then we want Z1 to be high and so on, right? And then the whole idea is that we find W's and B's such that this is true. And then we plug in a new image X for which we don't know the answer. And we get whatever Z's we get, and we try to guess based on the Z's whose picture it was.
If B is like a 6-dimensional vector, how do you add it to a 4000 something dimensional vector?
You don't. So here, right? So like this is like so here there is like a multiplication of, you know, like WJKXJ, and that's like 4096 things that you add up, right? And then here you're adding 1B, 1K. So like for ZK, you're at for Z1, you're adding this guy. For Z2, you're Z3, you're adding this guy.
Oh,
Right?
never
So
mind.
this, yeah.
Okay. Okay, so is it like basically you have like say a 64 by 64 matrix, and then you basically put it into a black box and you say the picture is like the actor of Z1. So you have like a 64 by 64 matrix, you put into a black box and you say, I want to get a matrix of 1, 0, 0, and then the rest are zeros.
Well, so kind of, except it's like ordinarily, like the term black box indicates that you don't know what's going on. Here, you know exactly what's going on, right? It's this formula.
Okay. Okay. But then like the algorithm itself adjusts the values of W and B?
That's right. So the trading process is like adjusting the values of W and B. Yeah.
Okay. Okay.
Yeah. So
Thank you.
so that part would be kind of black boxy.
Okay. Yeah.
All right. Cool. All right. There's like stuff in the chat. Okay. No. So the okay. So the question is like, are the H's optimized? No. So the H's are so kind of if the W's and the X's are given, the H's are just computed, right? So there is a formula for computing the H. So you can't like it doesn't really make sense to like simultaneously. I mean, you could if you wanted to, but like you optimized for the W's, and then the H's are just like intermediate results of the computation. Yeah, so they're not so they're not predefined, but if the W's are given, then together with then the X's just determine what the H's are. So people sometimes optimize layer by layer, it is true, but just don't think about this way. Even though like that's true and like it used to be more true than now, but this is like details. So just think about it in terms of there is a formula for Z's. It just so happens that this formula, it just so happens that this formula involves this kind of computing like intermediate results like H. But basically, like there is X's, there is the Z's that you compute, and this is the formula for Z's. It's just that this formula involves computing the H's before you compute the Z's. But you know, if you have a big formula, then like sometimes you want to do it like a little bit step by step. And then like you have, and then like it's analogous to what we've done, right? So like you have like whatever, like a formula, like if you have a formula like in physics, right? And like you know the y's and the x's, and you want to find the a, the b, and the c. That's exactly what's going on when you're trying to find the w and the b. Yeah, Alison, yeah.
Hi, we won't ever be asked to calculate W and B, right? Like we'd be given them?
No, like it's so like it's possible if you do like a very small neural network to just do it with like calculus.
Yeah.
So might have been a good idea for next year, actually, but no, like
Oh, oh, but
it's
not on this one, right?
no, good idea though. No, so like you could, right? So like if you imagine that the neural network is just like one X and then like one Z,
Yeah.
so that means that like literally Z is you know, like B plus WX and then sigma.
Right.
And then you have like one data point. So you have like, you know, like X equals to 0.5 and you want Z to be equal to 1. Yeah, like you can solve it if you wanted to.
Right. Okay.
But yeah.
Thank you.
Yeah. but like ordinarily, like the neural network is so large that you cannot do it by hand. Yeah. And then like we kind of informally just said that we want for Z to be like approximately 1 for this one and everything else is 0. We haven't actually formalized how to do that. Yeah.
Sorry, I'm just like thinking the formula through again. But
Mhm.
if you dot product something, you get a singular value as a result, right?
You mean like a one-dimensional, yeah.
Yeah. And
Yeah.
then how do you add it to a matrix that's like, say if there was 6 nodes?
You don't, so here it's like an element of a matrix, right? So like it's like B1K, right?
So you
So
add the, sorry.
so like this is also just like a single number. So the reason you can think of like the B's as like a 6-dimensional matrix, a 6-dimensional vector here, sorry, right? Is that you can also think of like this 6 dot products that you compute, oh sorry, the K dot products that you compute as a vector as well, right? So like you have like for each K, you have a dot product. So then you have like K dot products here, and then you have like KBs here, and then you can add them together as 2 vectors if you wanted to. But like B1K, it's like one single number.
So for, so like just thinking about like from going from X to H, how many weights are there? There would be 6
There's
or K
so weights
6?
would be like the number of connections between all the possible X's and all the H's. So if there's 4,000 X's, meaning like 4,000 pixels, and K capital K H's, then there is H times K W's.
And and each W is a
Sorry,
matrix?
4,000, sorry, times K. Sorry.
4 4,096 times K?
Yeah. Yeah, because like, like if every one of, like if there's like, a connection, which means a weight between every X and every H, that's like 4,000 H's, 4,000 X's, sorry. Sorry, 4,000 X's and KH's. So that's 4,000 times K total connections.
But wouldn't would there only still be 6 or K matrices?
So
Because
the 6 is the Z's, right?
right.
So we have connections between the X's and the H's, and then we also have connections between the H's and the Z's. So we have 6 Z's in this picture. So that means that we have K times 6 connections between the H's and the Z's. And
I guess
then
what I'm sorry.
4,000 times K connections between the X's and the H's.
Yeah, but I think I'm confused about what is like a weight. Like, are you saying a weight is one number in the matrix, or is weight
Okay, so a weight is the coefficient so like the weight between this and this is the coefficient by which I multiply X 4096 when I'm computing HK. So if I have like 4096 times K weights, it's convenient to store them in a matrix, right? So it's convenient to say, I'll just have this matrix, W1, that's going to be you know, 4096 times K. Like let's say K is like 100, right? So that's just convenient because then I can go like I want like the weight that connects like X at index 4 and H at index 2, and there it is, right? So that's one way of thinking about it, is like you have all those weights, you need to store them somehow. If it's like 4096 times k of them, then it's convenient to store them as a matrix. There's other reasons that it turns out good to think of them as a matrix, but that's the basics of it, is that like it's just convenient so that you can refer to them like that. And that is also how they work on the slides, right? So here, if you look at the formula, like I'm saying like W, so here the one is constant, and I'm saying like W, J, K for like different J's and different K's. So W kind of looks like a matrix as well.
Right. So then going back to like the code, would X would be it would be like npi dot random dot rand 4096. Wait, no, 60,
Yeah,
no.
yeah, that's
Yes?
that's right, yeah.
Okay. So then is it like 4096 by 1? Like there's
You could if
4096
you
bits?
wanted to, like it doesn't really matter. It's 4096 numbers.
So then
So like the
so then
idea
it'd
is
be
I
1
want to
by
be able
K.
one 496, no 4096, or at least in this situation, there's like 4096 dimensions in X because it's a 64 by 64 image.
Oh, and then when you dot product X with W, you get a 1 by K thing?
Yes,
Oh,
yes,
okay.
would, and H. So like when we're talking about H, sorry, that, and then like yeah, that's what you want because there's like KHs. So if you want to do it with matrix multiplication, which we have not done in class, but yes, you can do it. So when you so here the dot products that we compute are not quite that, right? So the dot products are like slices of W dot X. So here we're not taking like the entire W. We are saying like X and then like W, and then we choose, so here's everything, and we choose like a slice here, right? So we say like all the coordinates here, but just the 0 here. And then this is 4096 dimensional, and this is 4096 dimensional.
And that would be for the first one, the first H.
That's correct. Yeah, for H0, yeah.
Also, in the office hour on Friday,
Okay.
the notation, you had like 2 colons or something like that?
So
Or
yeah, so that was sorry, I don't really quite remember it, but so if
it
so
was like np dot W square brackets 0 colon K and then X.
W0 column K.
Yeah.
Yeah, yeah, that makes sense. So that's just because here I defined W1 like this, and back then I defined it like this. So I just had to have the 0. Because like here it's just like a dimension that's not doing anything because it's always going to be 0 for this one.
Is that like the number of hidden layers?
No, it's not really anything because so it's not really anything because at least kind of in this picture, you can't really do it uniformly for the different hidden layers because they have like different numbers of inputs, different number of outputs. So you kind of have to do it separately anyway.
Okay. Okay. Okay.
And sorry, I'm kind of glossing over this because those are like small details that I would not ask about.
Okay. So we can do dot product or matrix? No, just dot product.
Yeah, so like the matrix, I think I just mentioned on Friday, and as I said then, like it's not something I mentioned in lecture. The
Okay.
dot product I had mentioned in lecture, yeah.
Okay.
So,
Thank
but
you.
it's true that you could do it like as a matrix product, yeah.
Right. Thank you.
Professor,
Mhm.
I have a slightly irrelevant question.
Okay.
So for question 8 on 2024,
Okay.
like it asks you to use DP. I just want to clarify, like the solution you did for the lab, which is like purely recursion, that's not DP.
So I would I would, so the short answer is I would accept the recursive solution as dynamic programming. Like the difference is very small. So the only situation where I would not is if the question were literally like do both the recursive and an iterative solution, in which case like you can't, in which case like the recurrence is still the same, like the basic formula, if you remember, like you could just like go between that and this, and they're like basically the same structurally. So unless I specifically ask for both, you can do either, that's fine.
Like by both, you mean like both like the like tabulation and then recursion?
So like essentially like recursion with memoization
Oh,
is like basically the same as uh like like there is a distinction there, like if you think about it, but like it's like a very small distinction that like I would not care about,
oh, but if it is,
except if I ask for both.
but if there's no like memoization, which I think like in the lab solution you didn't do that either.
Uh that's possible, yeah.
So you still accept that.
I mean, I guess, but like doing memoization is like 1.5 lines, so why not just do that?
Okay. Okay, thank you.
Yeah. Okay, there's a question in the chat. So like the answer is like I would not, like unless I specifically tell you to do this or that, or like I tell you, you know, like it must be this complexity or something, where if you don't do memoization, then it would usually be exponential, right?
But you still
Okay.
accept that as a DP solution.
Yeah, yeah,
Okay.
yeah. Okay. So how much do we know for neural networks? So there is one question from that is related to this, to the neural network slide deck. That question is very closely related to one of the need to know slides. And I don't have a problem saying it because I already said that that's exactly what's going to happen. So that is what happened. Yeah, yeah, Allison.
Hi, I have a really stupid question. What's the difference between dynamic programming and recursion?
Okay, so so there's like two answers to this. So like what Eric was asking about, I think it was Eric. So the discussion before was about the fact that that you can like go between dynamic programming and recursive solutions, but recursion is like much more general than you know, specifically like prompts that are like amenable to dynamic programming in some way, right? So the idea is like you can have, you know, a recursive solution with memoization that's kind of like this. Right? And then you can have an iterative solution. That's kind of like this. And those are like structurally the same thing, basically, right? So you still have kind of this kind of equation and this kind of equation, right? So those are the same. And also in order to compute like memo at 3, what do? You compute memo at I minus 1 plus some memo at I minus 2 in the same way that that's exactly what's happening here, right? So like if those were already pre-computed, then you would just return like memo at I minus 1. Okay, it's plus memo at I minus 2. So I'll do like I. No. Right. So so those are basically kind of the same solution in some ways. It's just that one would be like referred to as dynamic programming because like you keep computing this array memo, and one is kind of recursion with memoization. Right? Recursion refers to kind of functions calling themselves. So here there's no recursion because there's no functions calling themselves, even though this is like basically the same algorithm.
I don't think like I couldn't hear you for like the past 20 seconds. I don't know if that's just me. Oh, actually, that probably is just me. So I think my internet is really slow.
Okay. All right. So yeah, so I wasn't really saying anything meaningful anyways. Like all I'm saying is like so what we were talking about before is that there's like two basically equivalent ways of doing this computation. One is called recursion with memoization, and one is called dynamic programming. But really they're basically the same. But recursion could be used in situations which you probably would not call dynamic programming.
Okay.
Right?
So they're
Because like
like,
recursion, it just means the function is calling itself. It doesn't
okay.
kind of refer to this specific idea of I can like pre-compute some stuff.
Okay. Thank you.
Sure. Right. Anything else?
Oh, sorry. Last semester you posted the first page of the exam. Would you do that again today or not?
Sure, yeah, I can do that. Yeah.
Okay, okay. Thank you.
Mhm.
Professor.
Yeah.
So like just for neural networks, right? In terms of what we need to know for the exam, this might sound like a dumb question, but is it just the need to know slides on the neural
Yes.
network? Okay,
Yes.
thank you.
Professor, I'm going through the binary tree stuff on the slides.
Okay.
On one of like there was a code snippet that you gave us. They initialized like all the numbers in the tree, but then they didn't initialize the end of the tree as nuns. Is that
Uh,
I feel like that's supposed to happen.
was it with like class node?
Yeah.
Then no, because by default the children are none.
Oh, right. Okay. Thank you. That's true.
Professor.
Yeah.
Could I ask a question? This might have just been an issue with my code, but when we did the Dijkstra algorithm in lecture,
Okay.
you know how we take from the priority queue the current distance and then also the node and then the previous bit if we need it?
Mhm.
Um, so okay, never mind. It's actually no, oh yeah. So you see how line 81 current dot previous equals previous?
Mhm.
how come that's before the if statement and not after? Because if it's already visited, we don't want to change what the previous is, right?
Uh, that is fair. I don't think it would matter because if it was popped from the queue, that's also good. So it would be the same. But yeah, like that's probably fair.
Do you think we'd be asked to implement, like, should we know how to implement the graph in both C and in Python, or would that just be a Python thing?
I believe we have implemented uh, Python and C in like lab 7, maybe.
Okay. Okay. Oh, sorry, one other question. Do we need to know how to implement heaps?
No, we have not done heaps.
Okay, thank you.
Sorry, Professor. We posted like a couple of questions in the chat.
Oh, um, how much do we need to know runtime complexity with regard to neural networks and data structures? I mean, so to the extent that we've done them in class, and potentially sometimes you see in previous exams kind of problem solving questions, kind of thing that we didn't do in class. I don't really think there is like anything like super complicated I could think of in terms of like the complexity of like neural network. Like there is like interesting stuff to do with linear algebra, but that's like not something that we've covered or that they could ask. So all there is like really like, like what's the complexity of like computing the neural network using for loop, and the answer is like, well, like you have as many terms to add as you have weights. So like whatever we did the computation with, 4096 times k plus k times 6, I guess would be the complexity, right? I don't think there's anything else. With respect to data structures, so kind of whatever we did in the lecture. Do you have any strategies for questions like raised to 21? Um, like that was just like a hard question. I don't even know how I did it. So uh, so I think kind of so first of all, like I don't think that it would be like super reasonable to ask the raised to 21 question if it hadn't been like actually an in-class example. So in this case, kind of the strategy would be to think back to like in-class examples. I think the way it was presented in class though, and this year it was in 180, was that like here's just like a recursive solution to the question of like, is this a winning position or not? So I guess then the idea was, and we had discussed it in class this year as well, if you go back to like, oh, like kind of the structure of the recursion there is kind of like depth first search. And then like for Q6A, I think the strategy was to just like recognize that. And it was in a way just like either you remember it from class or you don't, that you know, like both kind of the recursive solution for game 221. I don't think it's like super easy if you don't know this like this exact technique for games. Which kind of we had done in class. So it's more kind of like, did you remember that? And did you remember that what it was depth first search? So for question B, Q6B, um, the idea there was that, okay, like if you, I would expect, and I think that's actually what happened, is like the people who solved Q6A, they all did it recursively. And then like if you remember that you can actually do depth first search iteratively by having a stack of nodes yet to visit, then this is just kind of transforming the code to doing that, where instead of calling sum plus one, sum plus two, sum plus three, you put sum plus one, sum plus two, plus sum plus three on the stack, and then you repeatedly get the elements from the stack. So that would be kind of my kind of high level strategy of what to do. It's not like I'm not sure that like what I'm saying right now with respect to this is helpful, just because like it was like a genuinely challenging problem that quite a few people were able to solve. I think like less than 10% of the class. And then like it's kind of hard to give a strategy for solving like something that was like one of the probably most difficult problems I've ever given in an exam. So yeah. Do we need to know how to implement Dijkstra start to end, given that this is the first time that what do you mean this is the first time? We had done it in class. So uh, so the question is like, do you need to know how to implement Dijkstra? And so what I would say is that you don't in the past have examples where it was like implement Dijkstra from scratch. You had, however, examples of like implement a star with kind of some scaffolding of like you build it up by first implementing DFS. So I would not expect to like, it would be like maybe odd to say like implement just Dijkstra from completely from scratch. But like with some scaffolding, something like that, that could happen. Okay. Can you? Yeah, and sorry. So like I'm always asking kind of hypotheticals, and like it's definitely sometimes the case that I'm like I have no idea where you came up with that idea, and then I still answer it as hypothetical, and sometimes it's like, oh, actually, it's almost like on the exam what you're asking, and then I'm still answering, hopefully in exactly the same way. Yeah, you'll find out tomorrow which ones are which. And I'm not saying anything about like anything that's been asked in the last couple of days. So yeah, okay. So if I understand how to traverse a graph using DFS physical nodes, yeah, I mean like that's good. I think still, so like I don't think like I kind of regret putting certainly Q7 on the exam last year. At the same time, I feel like, like if you can kind of go over it and try to kind of write it eventually from scratch, that would be kind of like, that would mean that you're really good for everything, because that's like more difficult than probably anything else. Clarify the meaning of base template. Yeah, so what we're saying here is that we're computing Z1 as the dot product of X with a subset of the W's. And then we're computing Z3 also as a dot product of X with a different subset of the W's. So the subsets of the W's with which we're computing the dot product of X with are also of size 4096. So we can view them as kind of 64 by 64 images. And kind of the way we are using the network is we're saying if Z1 is high, meaning if X dot the subset of W's is high, then it's person one. And if Z3 is high, meaning the dot product of X with the corresponding W's that connected to Z3, then it's this person. So a different thing that we mentioned is that if the dot product between two vectors is high, that means that, other things being equal, those vectors are kind of pointing in the same direction. So they kind of look the same because if two vectors that are like images are pointing in the same direction, that just means that they're like a darker and lighter version of the same image, right? So in that sense, we're saying that the thing that we're computing the dot product of X with that makes Z1 high is kind of the template for the person who corresponds to Z1 being high. Okay. And then we visualize those templates. So like in this particular architecture, they look a little bit like faces, but not very much like faces. But if you think about computing the H's, where again, like it's like the dot product of X with one set of W's, dot product of X with another set of W's, and so on, then actually those sets of W's, when you visualize them, actually do very much look like faces. So that sometimes happens. So there was like one request, and I said yes to the request, and the H sheets are now printed. So yeah. And like the request is like on the comment. Yeah. So the subset of W's that should produce a certain Z based on input is the template. So like the template stuff, it's like an interpretation. So it's like an interpretation of what's going on. So you can just say like this subset of the W's, you can think of it as the template, right? It's like it's an interpretation. It's not like anything that you input. It's just that once you have W's that work, you can say, oh, like I'll interpret like this part of the W as that connects X to Z1 as like the template for Z1. All right. There's no other questions. Oh, okay. Allison has another question. Yeah.
Sorry, I had a general question on like graphs
Okay.
and like traversing through them. So what's the purpose? Like, why would you use it? Like, what do I get from doing breadth first search and depth first search?
Yeah, that's a good question. So one answer is that if the graph is given as a bunch of nodes, then if you want to just print out all the nodes, like what would you do? Well, you'll just like walk along the graph and discover new nodes. So one way of saying it is that it's a way of enumerating all the nodes. If you're looking for a node with a certain property, again, like if you just start from some node and you just need to explore the graph in some order. So that's what you're doing.
So is it like, how is it like, would it only be different from Dijkstra because Dijkstra there's an end and like you want to get the fastest, like you want the number of the nodes to visit to get to the end as fast as possible?
Well,
min-
so Dijkstra is different in several ways. So one way in which Dijkstra is different is that if all you want is to just, it's not necessarily actually just with weighted edges. You might be looking for shortest path where they're unweighted and you just consider all the weights to be one. So that's possible. So Dijkstra is really an algorithm for finding the shortest kind of the shortest paths or the length of the shortest paths from the source to everything, right? So you can use Dijkstra in order to simply explore the graph. However, that's not as efficient as traversing it because it would require you to look at the same node several times. Whereas if you're just traversing the graph, then like you look at the node once, you're not even going to check again. It's already visited, so you just discard it.
So for the specific question of like, I think 2023, where it was like friendship chains and like Michael Faraday and whatnot.
Okay.
Could you also use depth first search for that? If you're just looking at visiting all the nodes?
So if I recall, this was like longest friend chain or something, right?
Yeah, yeah.
Right. So you could, but it would be kind of annoying to find it would be kind of annoying to traverse because like you need to keep track of the length of the path, and it's not that easy to do.
And for a queue, you don't?
Oh, you do, like for both, like it's so like traversal is just like not the best way to do it, I would say. So like you can do it with Dijkstra, or actually kind of the intent there was to just like try all the possible chains and just try all the possible rearrangements of the nodes and then like find the longest possible one, which is actually a chain. Like that's, I think, the easiest one to do it.
Oh, okay. Also for
So
like
you
Dijkstra,
can also
sorry.
do, some people, you can also do like Dijkstra with like all edges being equal to -1 and then like the shortest path where like all the weights are -1 is like the longest chain.
Okay. Also for like depth first search and Dijkstra and like breadth first search, you only use it when you want to explore all the nodes?
Not necessarily. So it could always be the situation that you're just looking for a particular node, and once you found it, you just return. So that's possible if that's kind of the use case.
Okay. Also, if you use breadth first search, depth first search, and Dijkstra, you have to construct the data structure first, right?
Yeah, I'm back. Hello?
Hi.
Yeah.
Okay, I guess I'll just say my question again. For depth first search, breadth first search, and Dijkstra, you have to first create the graph before you can then traverse through it, right?
Yeah, I guess it was like created for you. Sometimes, as in the case of like Q6 in 2024, the graph is kind of implicit, right? So there is this notion of the graph of the positions, but it's not actually created. You can just like go to the neighbors by saying, oh, like then if I'm in position POS, then like my neighbors are like POS plus one, POS plus two, POS plus three. So it's not like the graph is not actually like constructed ever. It's just kind of a pretend kind of graph.
Right. Okay. Um, Also for the 2023 question number 9 about the cost on stepping on the steps,
Oh, yeah, yeah.
is that similar, like more similar to the coins question or the painting the houses question? Or neither?
Um, mm, okay. Sorry, let me just like reacquaint myself with the steps question.
All right.
Uh,
It's like
so each uh each okay, you can 1, 3 cost. I mean, I would say if anything, it's more like the houses, I guess.
okay.
Because so the reason I say that is because uh kind of with the coins or yeah, I don't know, maybe both. So like the reason the reason I say that is because like I suppose maybe more. Yeah, I think it's kind of similar to both. Uh, so uh, so like the way you would think about it, right, is you would say, okay, like the last step that they make is going to be like either one, or it's going to be two, or it's going to be three, right? And then you're just saying, okay, like if it's one, this is how much it's going to cost. If it's two, then this is how much it's going to cost. If it's three, this is how much it's going to cost in terms of a kind of n minus one, n minus two, n minus three, where it would be, right?
Right.
So in the same way with coins, you're kind of saying, if I'm making up the sum s, then the way I would make it up is like s minus denomination one, or s minus denomination two, or s minus denomination three. And then I have like the last coin plus I need to make up like either s minus coin one, or s minus coin two, or s minus coin three.
So would you go like bottom up? Like would you go from the bottom step to the top step, or would you like do it like houses where you start at the end and then you like say you assume you already know the minimum total cost to get to a certain step?
Oh,
And
it's in that way it's kind of similar, right? So like so like with coins, just like with houses, you actually do go from the bottom up, and then once you kind of if you're doing the iterative solution, right? You do first say, like uh this is like this is what they can do with one coin, and then only when you can fill out like the things that you can do with one coin, then you can compute like what you can do with two coins and so on. So like you're also going from the bottom up.
okay.
So it's just that when you're doing it recursively, you're doing it from the top down. And big thing with houses, like because like when you're calling the recursive houses function, you're calling it on like the entire array, right? And then like you're calling it on the entire array, and then like the recursive function calls itself from like a subset.
Okay. Okay. Got it. Um, Yeah. Okay. Final question. Sorry. Um, if there was a question of saying you start in like a matrix and you're starting at the top left corner, and then somehow you want to, or actually, like, would there be a question where you have like you know the website you showed in lecture?
Mhm.
Would there be a question where you start at a specific point and you want to get to the endpoint fastest? And like, what would you do like a graph and then like traverse through it to get there, or would you do like dynamic programming somehow to get there?
Could be. And I suppose you could do either. However, like we approached it kind of as a graph, right? But
Right. And so you would have to like write out every single node though, right? Like
uh,
pre-write out.
I suppose so. You could also do it, programmatically, right? So like if like if it's like literally a picture, then I guess like you would have to that.
Okay.
Yeah.
Okay. Okay. Thank you.
Yeah.
Sorry, just a very quick question. Like, all an A star is just like Dijkstra with like a heuristic, right? And it's like we're given the heuristic.
Or you need to come up with heuristic, yeah.
Oh,
Or you need to come up with heuristic.
sorry. Like, do I need to talk again?
So like maybe you're given the heuristic, or maybe you want to come up with it yourself. Yeah.
Okay. I see. Thank you.
Professor, about the A star. So with the priority queue, like at least in the example, I think in lecture or like from the slides, it showed that the priority queue, like the tuple had like three values, like one for the heuristic, one for the distance, and then one for the actual node. Um,
Yeah.
what is the priority queue comparing in that case?
I mean the prior so you mean like what is the priority?
Yes, yeah.
The priority is distance plus heuristic.
Okay. So how come then like do we need like like positions for both of them in the
Well, because
queue?
like you also want to compute the actual distance, and like distance plus heuristic doesn't count.
Oh, right. So the heuristic, so like the actual priority is both, but then next to it is also the distance because
Yeah,
we need the distance.
I mean the priority is the sum, but you also need the distance to compute the distance from the source.
Right. Okay. Thank you.
Hmm?
I have another question.
Mhm.
You said that we wouldn't need to do heaps, but like the
Right.
Dijkstra that we did in class uses heap.
Uh, so I said that you don't need to do heaps as such. It is true that underneath uh, the library heap queue uses a heap, but the way we use it is just as an implementation of a priority queue, right? So like we don't care about the fact that it's like underneath it's implemented as a heap. In fact,
Oh, okay.
we never said what a heap was.
Right. Okay. Okay. Thank you.
Yeah, so like what is also true is like sometimes people say heap when they mean priority queue, in which case, yes, we did do priority queues, but heap is actually like a specific way to implement the priority queue, and we haven't said anything about it.
Okay. Thank you.
Mhm.
Professor.
Yeah.
If we're asked to like create a data structure and like with all like the implementations of the functions for the specific abstract data type, do we need to like write that as like we're making a header file and then like a file for the functions and then a main file, or can we just write out the struct and then the functions, and that's it.
So you only need to separate them out if you're explicitly asked to do that.
Thank you.
All right, guys. Good luck. If I like wake up early in the morning and there's nothing urgent, I'll like post a Zoom link and we can chat again. Or I'll see you tomorrow afternoon. Yeah. All right.
Thank you, Professor.
All right. Good luck. Have a good night. Bye.
Good night.
Thank you.
Thank you. Have a good night.